All right, let's take a look at this particular problem. And we're going to use the design equation for machine design. So this shaft in figure 12.1 is part of a drive for an automated transfer system in a metal stamping plant. Gear Q, which is this one right here, delivers 30 horsepower to gear B, which is right there. Okay. Sheave D, which is this right here, delivers the power to its mating sheave as shown. The shaft carrying B and D rotates at 550 RPMs. We're going to use SAE 1040. And we're going to figure out the minimum size for this at the critical point. Okay? So, given P equals 30 HP, N equals 550 RPMs. The angle of the gears, psi, is 20 degrees. The pitch diameter of gear B, 16 inches. The sheave at D, the diameter of the sheave, don't do that. Okay, of the V-belt sheave is 10 inches. We get theta is at 40 degrees of the belt there. Okay, and that. We're going to use a design factor of 3. Properties. SAE 1040 cold drawn steel. SU is 80 KSI. SY 71 KSI. Now scroll down here. This is the coordinate system we're going to be looking at. Alright, so we got Y is up and down and X is side to side. We're going to get to a point where we're going to look down on the Y, and so we're going to look down this way on the Y, and then we're going to look that way towards the X. Okay. So we're going to use, let's start right, we're going to find D, the diameter at the critical point. And we got the sketches over here, and I'm going to do sketches all the time here. So solution, here's the design equation. D equals 32 n over pi times the square root of kt m over Sn prime squared plus 3/4 t over sy raised to the 2, and all of this is raised to the 1/2. Okay. Again, this is very similar to those other two, just with some modifications. So what we're going to do is we're going to find the shear, the moment diagrams, figure out, okay, we're going to find the max moment, assume a KT, find the torque. In order to do this, what we need to do is we need to find forces. Okay? So, this is where we're going to start. We're going to find forces on gear B. So let's do a quick sketch over here. So we have this rotating that way, that's rotating that way, and we got a torque B. This is Q, right? And then the bottom is B. So we're looking pretty much at this setup right here, just sideways. What we have is downward WRB, the radial, and then over here the force is WTB. tangential forces of this gear Q going to gear B. And we can find those. So let's go over here. Radial. WRB is the torque at B times tan phi. And we're going to call this FBY. Tangential at WTB, which is the torque at B over the pitch diameter at B over 2. We're going to call this FBX. So we need to find the torque, TB, and this equation is given 63,000 times the power over the RPMs. The 63 converts it to pounds. We're going to end up getting pound per pound inch. So 63,000 times 30 HP over 550 revolutions per minute. So we get TB to be 3,436 pound inch. So now we can find the radial and tangential forces. So now WRB is 3,436 pound inch times tan of 20 to get 156 pounds. Again, call this FBY. And then we have WTB, which is 3,436 pound per inch over 16 inches divided by 2, give 430 pounds. Call this FBX. Right, so now those forces are pretty much forces acting on the shaft at that location now. So what we need to next do is, scroll back up here, we have those forces. Now we got to figure out the forces acting on that sheave. Okay, so what we're going to do is do this. Forces on sheave D. Let me draw the shaft. So this is A, B, C, and D. What we have is a torque, TB here, and that'll be the torque over here. All right, so the torque A to B is 0, but then the torque B to D is the 3,436 pound per inch. All right, that torque from that gear is being distributed through that shaft to that sheave. Now let me draw a sketch over here. Here is that sheave D. Then we have F1. We have F2 from the V-belt. And the overall is FD, which is F1 plus F2. We can find FD from the equation I showed you before, 1.5 times the torque at D over 2. This is 1.5 times 3,436 pound inch over 10 inches over 2, and this becomes 1,031 pounds. And just to note, other formulas, F1 minus F2 is TD over D over 2 as well. Okay. And F1 plus F2 is 1.5 F1 minus F2. Okay. But just use this equation right here to find that force. What we need to do now is that's at that 40-degree angle, so we need to find the components. So f dx equals fd cosine theta, 1031 cosine of 40, and you get 790 pounds. F dy is fd sine theta, which is 1031 sine of 40, and you get 663 pounds. So the way I like to do it is, here is that vector VD. We go over, this is f dx, and then we go down, right? F dy, and that's that theta. So we've broken up the forces exerted on that sheave to the shaft now in the x and y coordinate systems. Okay. Now, let's take a look and create the shear and moment diagrams. So we're going to look at the horizontal plane, which is your x, and let's look at, I'll do different color, let's do purple, vertical plane over here. Oh. Okay. Let's do horizontal first, and then we'll do the other one. Okay, so we have up, RAX, that's the reaction, right? If I go all the way up, it's going to be this reaction here. We're going to need a reaction here. We know these forces now, right? We know this force, and we know this force. And again, we're going to be looking at the forces acting in that direction. Perfect. Okay. So RAX. Then we have FBX, which is 430. We have our CX reaction, and then we also have FDX, right? Which I just calculated as 790. Okay, because we're looking at it in the x direction. Okay, so sum the moments at A, set it equal to 0. We have minus 430 pounds times 10 inches minus RCX times 20 inches plus 790 times 26 inches equals 0. We find this reaction to be 812 pounds. And let's do some of the forces in the x, set it equal to 0. Upward is positive, RAX minus 430 minus 812 plus 790 equals 0. RAX equals 452 pounds. All right, so let me write those in. This is 812, 452. Now let's do the vertical plane. We have RAY. We have FBY, which is 156 pounds. We have RCY, and then we have FDY, which is 663 pounds. So we can sum the moments at A, set it equal to 0, positive 156 times 10 inches plus RCY times 20 minus 663 times 26, we get 0. RCY equals 940 pounds. 940. Sum the forces in the y, set it equal to 0. Up is positive. minus RAY minus 156 plus 940 minus 663 equals 0. RAY equals 121 pounds. Whew. Okay. We have now found the forces exerted from the gears, the forces exerted on the sheave, the reaction forces in both directions, right? And now what we can do is a shear in moment diagram. So let's do the shear and the moment. I'll keep it in a similar spot. Move it up here. That's fine. Well, no, I'll keep it consistent. Oh. And I'll probably have to go down more. So there's going to be 3 sections. So let's draw these in light blue. Got to draw that more. And I'll draw that more. Okay. Okay. So those are our A, B, C, and D locations. Let's do orange. So this is going to go up to 452. Going to go over. Right. This is 452. It's going to go down. This is going to hit 22. It's going to go over. And then we're going to go down to minus 790 because this needs to come back up. There's our shear diagram. Let's do this one. So here RAY is going to go downward. We're going to go over. Then it should go down more, right? Yep. It should go down. This is going to be negative 277. This was negative 121. It's going to go over. Then it's going to shoot all the way up. This is 663. Goes over and it's going to go back down. There's our shear. So V. This is M. V. M. Okay. Okay, now let's do our moments. So this is going to start here, and it's going to go up right here. So that's 452 times 10, right? So this is 4520. Then it's going to go up. I don't know quite the angle, but I'll do this to right there. And that is 4740, right? Because that's going to be 22 times 10 added to 450. Let me start it again. It's 22 times this distance, which is 10, and you're going to add that to 4,520 to get up there. Okay. Then it's going to go right back down to 0. Over here, it's going to start here. And it's going to go down to here. Let me make this a little bit bigger. Let me extend all of these. This number is 1210, right? So 121 times 10. Then it's going to go down like this. Here, this is going to be 3980, and that's going to go back up. Okay. This is found by taking the 277 and multiplying by 10, right? So this gap in between, 277 times 10, and you add it to 1210. Okay, and it's negative, that's why it goes down below. So there's our shear and moment diagrams. Okay, why do we need this? Because in this fundamental equation, way up here, that is the max magnitude in between. And that's what we're going to do right now. So you can clearly see that at point C, right? This point right here. Let me do that in red. Let me undo. Go back down here. Point C has the highest moment in both cases. Okay? So that is where we're going to find the moment. If you weren't sure, you'd have to calculate the moment at every point. So M is going to be MC, which is going to be square root of MCX squared plus MCY squared. This is 4740 squared plus 3980 squared, and this becomes 6189 pound-inch. And this is C, right? So the torque at C, which we talked about before, was 3436 pound-inch. So we now have the moment with torque. In that diameter equation, we now need to find Sn prime, which is the actual endurance, which is the endurance times these factors that we talked about way back in, I think, chapter 3 or 5. Sn we find on figure 511, and we get Sn to be 30 ksi. Let's assume Cm is 1, CST is 1, CR is 0.81 based on 99% reliability. And we're going to guess a CS, 0.8, and if it's wrong, then we'll have to adjust. Okay, and I'll show you how we do that. So now Sn prime is 30,000 times 1 times 1 times 0.81 times 0.8, and we get 19,440 pound-inch squared. And the last thing is KT. And what we're going to do here is we know that there's a torque involved. Go back to this schematic here. Let's zoom in here. So we're looking at this point right here. We know we went from a big diameter to a small one. There's probably some sort of fillet. There's a bearing in there. There's torque. If you go and look at stress concentrations, you'll find a graph. And you need those radiuses. However, let's pick... We're going to assume in this particular problem a KT of 2.5, kind of on the high side. Okay, and you can change that to see what that effect does. All right, but let's pretend that we got a high stress concentration value, which will actually make a bigger diameter. Okay. All right, and then again, this is the equation that we're going to solve. And I didn't do it. I did it in programming, and I'll show you. This is squared. It's 3/4 t over sy squared, and the whole thing is to the 1/3. So let me show you my programming code so you can see how I did this. It's easier for me just to program it than try to do it by hand. And then I can check as I go, and then I can modify it. Okay. So here is our givens. We got P, which is your horsepower, RPM. This is your, hold on, what was 20? PSI. Did I use 20 somewhere? I'm not sure why I had that. Oh, sorry. See, this is why we do nomenclature. This is why I did it. So PSI, that is your your angle 20 degrees for your gear. Okay, this is your pitch diameter. This is your diameter of your sheave. This is the theta or angle of the V-belt. This is your design factor. Okay, so again, don't do what I just did. Make sure you put nomenclatures in there. Okay. Properties, we're using cold steel, SU 80,000, SY 71,000. I assumed a KT of 2.5. Here's my endurance calculations: SM, CST, CR, CS, SN, and then SN prime. From the paper, all right, this is the calculations that we found. So the moment was 6,189 and the torque was 3,436. And then what I did is I split this up into terms. So term 1 is the KT term. Term 2 is your TY over SY term. And then left-hand side is 32 times N over pi. And then I put that into my equation here for D. Okay. Now, let me run it, and I'll talk about the last section, and I'll show you. So we get about 2.89 inches. So 2.9 inches. Okay. Now, there's equations in the book that we can use to find CS. Okay. So if the diameter is less than 0.1, then CS check is 1. If it's between 0.3 and 2 inches, this is the equation that we need to use to find CS based on your diameter. If it's greater than 2, this is the equation you use. So what you can do is you run it, right? You check. Our guess was 0.8. It's pretty much on the money. Okay. So say I went up here and I said, well, let's do something crazy. Let's do 0.2. Okay. We run it, and look, that doesn't match, right? So you need to keep changing this until that matches. All right. That's pretty close. Okay. So that's the diameter we need, 2.9 inches, or I'd go maybe 3 inches, just to be safe. Okay, especially with KT. Like if we increase KT, say we went to 3, run it again, see we get 3 inches. Okay, so we know that there's some sort of stress concentration in there, but we can use 2.5. That's pretty good. Sometimes you got to make that assumption because you don't know those diameters. So just pick something. All right, so let's go all the way to the beginning. So we had this particular system. We had gears, we had a V-belt. And the way to do this is you need to find all the forces on that shaft. And if they're gears, we have equations to convert those forces from the torque and the horsepower. Same with the sheave. And then once you find those forces, find your reaction forces. Okay, that's what we did here. Reaction forces. Then we found our shear and moment diagram and our torque. The moment diagram is used to find your max moment. Use that moment in your equation down here. Find the torque at that location. And then now you've figured out what that diameter is at that particular spot. All right. If you have questions, let me know. But this is the standard procedure. Thank you.